Now, calorimetry, we're going to use those two key equations derived on the previous slides here, and the first application is bomb calorimetry. Here, we have a rigid container, so constant volume, with a combustible chemical like benzene here. Benzene reacts with oxygen in the bomb, or just rigid container, making carbon dioxide and water. When we're describing that chemical reaction, it's useful to define a quantity called delta sub R U. So delta sub R for a chemical reaction, the R subscript here means reaction. So R for reaction. And we define that to be equal to the energy of the products at a given temperature and pressure minus the energy of the reactants at that same temperature and pressure. And the definition here means that we use the stoichiometric number of moles. So for this reaction that we wrote down, it's going to be the internal energy of 6 moles of carbon dioxide at a given temperature and pressure, and 3 moles of liquid water at a given temperature and pressure, minus, again, subtract the energy of 1 mole of benzene, plus the energy of 15 halves moles of O2. And this is going to describe what's the change in energy if I do this conversion. Convert 1 mole of benzene and 15 halves moles of oxygen into 6 moles of CO2 and 3 moles of H2O, starting and ending at that same temperature and pressure. When we're doing the calorimetry experiment, we can describe it by a constant heat capacity C near room temperature. I'm not specifying if this is at constant pressure or constant temperature. Probably doesn't really matter. In this case, though, the calorimeter here, this whole thing is the calorimeter. And the calorimeter is just freely in the room at, say, a constant pressure here. So arguably we should say that this is CP here. The calorimeter out here is just going to accept a certain amount of heat that was released from this chemical reaction going on inside the bomb. And that's what we see here. So yeah, maybe CP is better because the water is here at constant pressure, say 1 atmosphere or 1 bar. Now let's see how that works. So we'll apply the first law, determine delta RU from the given data. Okay, the first thing we need to solve this problem is that the bomb has a constant volume. So naturally, we're going to want to use this equation. Delta U is Q plus work non-mechanical. And that's true at constant volume. In the bomb calorimeter here, we don't have any resistors or anything like that. So we just have delta U is equal to Q. And that describes what's going on inside the bomb. So the change in internal energy inside the bomb is equal to the heat that is released or absorbed. Now, that's nice. So what we're going to be able to do now is measure this heat and use that to get delta U. How are we going to measure the heat? We're going to measure the heat flow into the surroundings. So Q of the system is equal to negative Q of the surroundings. Because again, it's just the flow of energy is heat. So if Q for my system is negative 100 joules, the energy that flows into my surroundings as heat is plus 100 joules. Okay, then the heat flow into the surroundings, Q sur is our Q cal. So the surroundings are our calorimeter, so we can say, again, just plugging this in, Q sys is equal to negative Q cal, which is equal to negative CP delta T. And that we can just plug in and solve. So the change in temperature in the surroundings here tells us how much heat flowed into the surroundings using this definition. So we have negative 8.782 kilojoules per Kelvin times 25.67 minus 21.95. Again, 1 degree Celsius is equal to 1 Kelvin when we're talking about changes in temperature. So this is also the change in temperature in Kelvin. Sometimes people get tripped off about those units canceling, but they will cancel. So Q system so our final answer here, the heat flow into the surroundings here was positive, so the heat accepted by the calorimeter was positive, the temperature went up, a positive amount of heat went into the surroundings here, but with respect to the system here, this was a negative amount of heat. There was energy flow from system into surroundings, so that makes sense that this would be a negative sign here. So from our equation here, now we know that the change in internal energy of the system here was negative 32.669 kilojoules. Our final step is determining delta RU. So delta RU is an intrinsic quantity. It depends on basically the moles. The way this works, again, based on how the equation is defined, is that delta RU is equal to, it's basically what delta U would be divided by 1 mole of reaction. So it's how much the change in energy of the system is for every 1 mole of reaction. 1 mole of reaction, though, is 1 mole of benzene consumed, because the coefficient is 1, 6 moles of CO2 produced, 3 moles of H2O produced, etc. So here we can say that if we take our delta U, negative 32.669 kilojoules, and divide it by 0.01 mole benzene, times basically 1 mole benzene for every 1 mole of the reaction, that will give us our overall delta U of the system here, or delta U of the reaction. So again, if we were measuring this conversion factor here did nothing here, but it is important. Let's say that we measured negative 20 kilojoules over, and we had 2 moles of CO2 produced, then we'd have to apply a times 6 mole CO2 divided by 1 mole reaction, because the coefficient in the balanced chemical equation is 6 there. So the coefficient in the balanced chemical equation does come in here when we basically convert from moles of a substance, here say CO2, to just the overall moles of reaction. In this case, the final answer is negative 3,267 kilojoules per mole. That should make sense. This is very exothermic, right? Negative delta U is very exothermic. From Gen Chem, if we have an internal energy, reactants, products here, we could think about like a reaction coordinate diagram with what the activation energy is here. But since we saw that energy was released, this right here is our delta RU, basically. The difference arrow, this is the down arrow going from reactants to products because the products are more stable. It's an exothermic reaction. All those sorts of types of things are really useful here. So overall here, calorimetry tells us what the change in energy is for different chemical processes. This will give us information about the energy of reactants and products, which is critical to understanding chemical bonding and other chemical phenomena. Other types of calorimetry to be aware of are constant pressure calorimetry. So there's a lot of different approaches. One from like a chemistry 120 lab is this sort of coffee cup calorimeter idea, where we've got stuff going on in water. We measure the change in temperature and use that to infer the difference, changes in energy and so forth of what's going on in our system. It's important that since we're at constant pressure, now we want to think about delta H is equal to Q plus work non-mechanical, right? That's going to apply always at constant pressure. And in this case, right, like this type of coffee cup calorimeter, we don't have any resistors or anything like that. So in this case, delta H equals Q. And we can proceed just like we did before in our bomb calorimeter, but now use the heat flow to determine delta H. There are other cases here where we're actually going to cut the flow of heat entirely. We're going to arrange the system so that Q equal to 0, and we'll measure everything by doing work on the system or surroundings to basically ensure that no heat flows. And in that case, we'll be able to set Q equals to 0 and just measure the work and use the work done to measure delta H. So a lot of approaches, but all coming from this basic equation. Okay, from doing a variety of these calorimetry experiments, we can start to get a picture of what these energy differences look like in real chemical reactions. So let's look at the nice example. H2 plus O2 goes to H2O. Now, we know that delta RU at 0 Kelvin is negative 477.9. And if we, again, use some rigid adiabatic walls, we can measure the amount of work that we need to do to go from 0 to 300 Kelvin, similarly for reactants and for products here. What does that mean in terms of our energy level diagram? I'd encourage you to take a minute to try this by yourself. You can sort of do this from prior knowledge, see what you could get for where these different energy levels should go. The type of diagram we want is going to be one where we have like reactants and products, and we want to also specify how far apart the energy levels are in a cartoon way, sort of like we would have had from exam 1 a little bit, right? If one has more closely spaced energy levels, we should say that. Okay, so I'll show you what I would draw here. So first, at 0 Kelvin, that's important because there we know we're all in the ground state. So from this 0 Kelvin delta H, and I'll write U, or maybe this should be molar energy reactants here. Since this is a negative delta U, I know the products are lower in energy. So these are my products, 2H2O gas, my reactants, 2H2 plus O2, all gases. And the products are lower, and I actually know exactly how much lower the products are. I know that this arrow right here, going from reactants to products, is equal to, has a length of negative 477.9 kilojoules, or kilojoules per mole, because we're per mole of reaction, basically. So the products are this much lower in energy. This is a very sort of exothermic reaction. Now, what other information is on this? Well, one thing we might want to know is which one of these has more closely spaced energy levels. That we can actually tell by just looking at the moles of gases. In general, more moles gas equals more closely spaced energy levels. And that's because those translational levels are the closest spaced. Those are much, much closer energy than all the other levels. And only gases have translational levels. So in general, the best way to figure out the more closely spaced is that in this case, I have 3 moles of gas. So I have basically 9 translations, because they can translate in each of X, Y, and Z. Here I only have 2 moles of gas, so I only have sort of 6 possible translations. So in general, more moles of gas gives me more of those translational levels because I have to pick translational levels for 2 moles of H2 and 1 mole of O2. That's going to multiply them and give me overall a denser set of energy levels when I have to specify all those quantum numbers compared to just 6 quantum numbers here for translations in H2O gas. So my reactants here are going to have more closely spaced energy levels. Products over here, slightly further spaced energy levels. The closeness of the energy levels we'll see is really going to give us information about sort of entropy, which we don't need to know too much about yet, but that is where that's gonna go soon. Where are all the particles at zero? All the particles at zero are in the ground state. So 0 Kelvin. At 0 Kelvin, everyone has to be in the ground state. At 300 Kelvin, now we're going to get some excited particles. So I'm just going to put a couple excited particles in each of these. That's what changes at 300 Kelvin. What's important to note from the scale, which isn't even quite accurate, is that it's not, doesn't change a ton here. I mean, that we do excite the particles, but on this big picture scale where we have 477.9 kilojoules per mole, not a ton of changes here, just because we can see it only took 17 kilojoules. So there's only 17 extra kilojoules of energy here in the reactants and only 15 kilojoules extra of energy in the products. So really, for the perspective of, the energy change of a reaction, there's really not much difference here going from 0 to 300 Kelvin because it's still so, very close to just the difference between the ground state energy levels, just because these are so far apart. This is a gigantic amount of energy, and so this little bit of energy that it took to heat us to 300 Kelvin is not a huge factor. We can then calculate delta R at 300 Kelvin. We can do that by basically so we can sort of think about this cycle here where what we want to figure out is what is the difference in energy at 300 Kelvin. So this is basically delta RU at 300 Kelvin. That's this process. And that's equal to, I can add up, first I do this process, take the reactants from 300 to 0. Then I do this process, take reactants to products at 0, and then warm the products back to 300. This is my delta RU of 0 Kelvin, which I know is negative 477.9. 300 to 0, it took 16.7 kilojoules to go up from 0 to 300, so this process takes negative 16.7 kilojoules, and this process here, 0 to 300, takes plus 14.9 kilojoules from the given information here. So if I add those three arrows up, I get this net process. I can think about reactants to 0, convert from reactants to products at 0, then go up to products at 300. Those three steps are equal to the delta RU, just reactants to products at 300 that I want. So I can say delta RU is equal to negative 16.7 plus negative 477.9 plus 14.9. And so delta RU is equal to, and the final answer here, negative 479.7. Yeah, so again, just like we expected, not much difference here. Really, the main difference between reactants and products is the different ground state energy levels. Those ground state energy levels, if we think back to exam 1, are really related. The ground state energy is sort of governed by the bond strength. If I have a stronger bond, if I just draw what like a stronger bond would look like, if I have a stronger bond, I'm going to have a deeper energy well here, and so this And so from these thermodynamic experiments, we can see that since all this, right, as we increase temperature, we're going to start occupying the translational levels, the rotational levels, maybe even a little bit vibrational levels. But we can see that on the grand scheme of things, this didn't make a big difference. It's still about negative 477, negative 478 kilojoules. The different occupation of these different energy levels made only a very small difference to the overall delta U. The overall difference, the overall reason this is an exothermic reaction is just because the products have a much more stable ground state electronic energy and therefore much stronger bonds. So products, stronger bonds, lower ground state energy. As simple as that is what comes back just from doing all these experiments. It's very useful to know about how energy is distributed in the reactants and products, and that affects a lot of properties of them. But when it comes to just knowing what the change in energy is for a reaction, really it's all about the differences in bonding. That's what we get from experiment, that's what matters the most.